Hello friends, welcome to Silent Learning. In this lesson, we will understand how a transformer works in a clear and simple way. No long words, no stress, just pure learning. Now I focus on the sentence the cat sat on the mat. It was warm and soft. A computer does not understand words, so we convert them into numbers. Here I use a three-dimensional vector for each word to keep the idea simple. These vectors are called static embedding because we set them by hand and keep them fixed. Now let's say we stand at the word it in the line and we want to find out if it refers to the cat or the mat in the earlier line. For this we use cosine similarity to check the closeness between two vectors x and y. Here x is the vector for it and y can be the vector for cat or mat. In this formula, we first take the dot product of x and y, then we divide it by the product of the length of x and the length of y. We divide by the product of the lengths because we want the similarity in the direction only. If one vector is long and the other is small, the long vector will control the result and the score will not show the true direction match. The part in the bottom acts as a normalization step that keeps the scale equal for all vectors. If the score is near 1, the words are more close. If the score is near 0, they are not close. Now you could see the similarity score through this animation. The initial vectors are random and we can adjust them based on the needs so that they become more clear and more meaningful. Here we can see that the similarity score of it with cat is 0.63 and with mat it is 0.81, which is higher. This means it refers to the word mat in the earlier line. This happens because we set the embedding by hand in a way that make it more close to mat. But wait, in a later part, if the line change like this, the story also changes. In that case, it refers to the cat, but our fixed embedding still make it close to mat. So this idea does not work in all cases. So what idea will work here? The answer is that we need a dynamic embedding that can update itself based on the need of the line at the point in time. The attention system in the transformer model create a clean dynamic embedding that changes with the line. Now I take the same example again with the same static embedding for each word. A transformer model uses three weight matrices called query, key, and value. These matrices start with random values and the model learns the correct weights during training. We now take the word embedding vector and multiply each one with these three matrices. This gives us the query, key, and value vectors in order. At this point, all word embedding vectors turn into three new forms. The query vectors shown in orange, the key vectors shown in green, and the value vectors shown in blue. Now let us come to the main question. What are the query, key, and values here? The answer is simple. The query is like a small voice that asks each key vector, how close am I to you? The similarity score tells us how close the query is to the keys. We can see that the similarity calculation of one query does not depend on the other queries. This means the model can do this step in parallel. But when we use parallel work, the model does not know which query comes first. To keep the order, we add a positional embedding to the input embedding. This lets the model understand which vector comes first in the sequence. So now we stand at the word it, and the query at this point asks each key vector how much I am related to you. The dot product give us the score that show the closeness. The score help us see if it is close to the cat or mat at this point. But these scores are just raw numbers. Softmax change this raw number into clean probabilities. So now each number tell us how much the word it pay attention to each other word. This is why we call them attention score. They show where the model is looking and how strong that focus is. Now we multiply this attention score with the value vector to get the final values. These final values vectors are the dynamic embedding and they change based on the need of the line. Now we can check the similarity of those words with it and we can see that it is now more close to cat. If the next like make it refer to some other words, the model will create a different dynamic embedding based on the need of that line. But wait, till now this is not a neural network. Why? The reason is that we only use simple linear steps so far and there is no non-linear changes in the process yet. For this part, the transformer model uses a point-wise feed-forward neural network. Point-wise means the same feed-forward network is used for all value vectors. Now we pass all value vectors through this point-wise feed-forward neural network in order, and the output gives us a non-linear and more rich dynamic embedding. This is one layer of the transformer model, and we can place many such layers in the transformer encoder to get the final embedding. This is the main idea of the transformer model, and you can process other time series data in the same way. For example, think about a weather time series. In the input vector, the first part can be the temperature, the second part can be the humidity, and the third part can be the rainfall. The full sequence can be the different times of the day.